We're going to take a theoretical look at the bonding that occurs in the molecules that we've been studying. And we're going to use the valence bond theory in order to help us to understand what is happening at the molecular level. Based on this theory, a bond arises from the overlap of two atomic orbitals, each holding an electron. This gives rise to a molecular orbital where the two shared electrons will be found. Let's look at bonding in the following scenarios of H2, F2, and HCl. In order to study these bonds, we need to understand where the electrons are in each of the atoms. And in order to do that, we need to know where the valence electrons are in a particular atom. So in hydrogen that has one electron, it's got that electron in a 1s orbital. In fluorine, an atom with 9 electrons, there are 2 electrons in the 1s, 2 electrons in the 2s, and 5 electrons in the 2p orbitals. For chlorine, we could draw an energy diagram. I'll just write the electron configuration here. It's got an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. So let's just use this information to study the bonding in each of the examples given here. We want to study the bonding in H2, so it's a hydrogen atom bonded to another hydrogen atom. The atomic orbitals for this molecule are 2 s orbitals. So what we are doing when we form a bond between 2 hydrogen atoms is we are overlapping these 2 1s orbitals to form a molecular orbital of H2. And the molecular orbital is determined from mathematical addition of these 2 wave functions. And as you know, our study of wave functions has been more simplistic. So what I'm going to show you is the resulting molecular orbital. So when these 2 orbitals combine, okay, we end up with an oval orbital. The nuclei started in the center of each of the 1s orbitals, and now they are at some distance from one another within the molecular orbital. So they'll never get too close to one another because they do repel. Now in a molecular orbital, we know that there are 2 electrons, and this theory exists because, as you know, we can't actually identify the position of electrons. And when we show our molecules like this, we're kind of putting the electrons in a fixed position right between the 2 nuclei of the atoms. In reality, these 2 electrons that are being shared are going to be somewhere in this space of the molecular orbital, which is the same concept we were using when we were studying the atoms. Now, to form the molecule F2, which also has a single bond, the overlap is going to be between 2 p orbitals, because the electron that is on its own is in a p orbital. So when 2 fluorine atoms bond, the overlap comes from the overlapping of their 2p orbitals. So these orbitals are going to combine. These are the atomic orbitals, and they're going to combine to form the molecular orbital. Now when waves combine, as you'll learn in physics, we can have what is called destructive and constructive interference. When we have constructive interference, the waves get larger, and when we have destructive interference, the waves get smaller. So what this means for the addition of these two particular orbitals is we're going to have some constructive interference in between these two, and we're going to have destructive interference to the outer lobes of the p orbital. So what we're left with is a molecular orbital that looks something like this. Mine's not perfectly symmetrical, it should be a bit more symmetrical. The nuclei of the fluorine are still at the center point of where the p orbitals were. So as we can see in this molecular orbital of F2, we're more likely to find the electrons right in between the two nuclei, and there's less likelihood to find them in the outer lobes. Now when we look at the molecule of HCl, the hydrogen's electron is in a 1s orbital that's looking to overlap, while in chlorine, similar to the fluorine, it's in a p orbital, this time a 3p orbital. So what we have here is we have an overlap between an s orbital and a p orbital. And these are the atomic orbitals once again, and we're going to form a molecular orbital. There's constructive interference from this side of the p orbital to the s orbital and destructive to the other lobe. So we end up with a bit of a lopsided p orbital. The nuclei from fluorine was here, so the nuclei from fluorine is going to be here in this molecular orbital. The nucleus from hydrogen is here, so the nucleus from hydrogen is going to be somewhere over out here. The pair of electrons that are being shared are going to be found somewhere in this space. Now, each of these orbitals has arisen from direct overlap of the orbitals. So these orbitals are able to directly come in contact with one another, and we call these kinds of molecular orbitals sigma bonds. They arise from direct overlap. Now, there's another type of bond that we're just going to discuss briefly at this stage, and this is called a pi bond. Anytime you see a single bond between two atoms, it is a sigma overlap that has occurred. And anytime you see a double or a triple bond, it has arisen from an indirect overlap of two orbitals. Right here, we're looking at a molecule of C2H4, and there's a double bond between these two carbon atoms. The second bond in this molecule has arisen from a pi overlap, whereby we have two p orbitals that are parallel to one another, and they cannot come in direct contact with one another. So if you look at two p orbitals, they cannot completely overlap with one another. The reason for that is because of the location of the nuclei. It's impossible for these two orbitals to come completely in contact with one another. So what occurs instead is a sharing of the electrons through space. So these are the two p orbitals that can't directly overlap. So these are the atomic orbitals. Each of them have an electron in them, and the overlap that's going to occur and the resulting molecular orbitals are something like this. Okay, so we're going to have an area where electrons can be found above the two nuclei and below the two nuclei. So the nuclei are in the middle here. Now, the examples that we've seen so far have been simple examples of bonding, where no hybridization is required in order for the bond to form. Now what we're going to start looking at are molecules that need to do what is called hybridize in order to prepare themselves for bonding. What we're going to do to start is look at an example of carbon. Carbon's energy diagram looks like this. Carbon has a total of 6 electrons. So it's got 2 in the 1s, 2 in the 2s, and 2 in the 2p. When we look at this energy diagram, we can see that at the moment, carbon is prepared to form 2 bonds. It's got 2 orbitals holding 1 electron that is available for overlap with another orbital. In your study of carbon in biology and in basic chemistry, you may already know that carbon always forms 4 bonds. So clearly, from its energy diagram, at the moment, it's not prepared to do the bonding that it normally does, forming 4 bonds. This occurs with a lot of different central atoms, where they need to do what is called hybridize in order to prepare themselves for bonding. Hybrid means a mixture. So what we're going to be doing is we're going to be combining orbitals to form what are called hybrid orbitals. Now, one of the most important things to know about hybrids is however many orbitals you put into hybridization is how many hybrid orbitals come out. So let's look at
Mixing an
Sp
s orbital with one of the p orbitals generates.
If we take s and p orbitals and we combine them, we're going to get 2 sp hybrids. Now, the way that those are going to organize themselves is in a linear formation. And we'll talk about that more as we go. Let's look at Sp2 hybridization. Think about it for a moment. If we have Sp2 hybridization, we're going to be combining 1 s orbital with 2 p orbitals. So we're going to end up with how many orbitals? 3 hybrid orbitals. So let's look at that. We've got 1 s orbital combining with 2 p orbitals. They hybridize to form 3 hybrids, all called Sp2, and they're going to organize themselves in a trigonal planar arrangement. Now, I hope you're starting to see the connection between the VSEPR shapes, the electronic geometries, and the hybridization. Let's look at Sp3 hybridization. I combine 1s with 3 p orbitals, and I'm left with 4 Sp3 hybrids, and they organize themselves tetrahedrally. We've got 2 left, and now we're starting to bring in the d orbitals. So I'm taking 1s, 3p, and a d orbital, and I'm hybridizing them to form 5 hybrids that will organize themselves in a trigonal planar geometry. Trigonal bipyramidal. The last hybridization that we can have is Sp3d2. We're combining 6 orbitals, so we'll get 6 hybrids that will organize themselves in an octahedral arrangement. So this is a nice summary from your textbook. It shows you which orbitals you're combining, the hybrid orbitals, and then it connects to the shape of the electronic geometry. Let's see this in action with some molecules. Now, one of the most important things is that you have to start with the Lewis structure in order to be able to predict what kind of hybridization is going to occur in a particular molecule, because it's the electronic geometry of the molecule that's going to help you to decide how many hybrids you need and therefore what hybridization needs to occur. So what we're going to be doing here is showing or demonstrating hybridization in molecules. And the hybridization occurs of the central atom. So let's look at a molecule of CH4. This is CH4, and we've already talked about and shown the energy diagram for carbon. with its 6 electrons. Now when we look at the Lewis diagram here, we see that it has an electronic geometry that is tetrahedral. There are 4 total electron pair domains around the central atom. So this tells us that the hybridization that we'll need for this particular molecule is Sp3. We need 4 hybrids, so the only possible way to get 4 hybrids is to take 1 S and 3 P orbitals. Now, when we hybridize, we're just going to be hybridizing the valence orbitals. So I'm going to blend or combine these orbitals together, this S and these 3p orbitals. So the 1s orbital is still going to remain the same in the carbon after hybridization. Now, as you know, when we take 4 orbitals, so 1s and 3p orbitals, and we hybridize them, we're going to be producing 4 hybrid orbitals. And as you saw from the little video, all of the orbitals are exactly the same. So they're now going to be the same energy. So these orbitals are going to be called 2sp3. And just like we place the electrons in the energy diagram of an atom, we can now place the electrons in the hybrid orbitals. So from the orbitals that we hybridized, we had 4 electrons. So now those 4 electrons, because these orbitals are now all at the same energy level, are going to be placed singly in the hybrid orbitals. So what we can see is, by hybridizing, carbon has prepared itself for bonding in the CH4 molecule. It's redistributed its electrons so that it's able to overlap with the 4 1s orbitals from the hydrogen. So the last thing that we're going to do is show the electrons, and you can use another color, or you can use sort of a dashed arrow. These electrons are from hydrogen. Okay, so what we've done here is we've modeled the bonding in carbon. Carbon hybridized, those are its electrons, and then there's overlap from the 4 hydrogens. Okay, so carbon took its 1s orbital and its 3p orbitals, and it hybridized. They organized themselves tetrahedrally. And then what we have is we've got the hydrogens come in, the 4 1s orbitals come in and overlap to form bonds similar to what we were looking at before in HF. Okay, let's look at another example. Let's look at SF4 this time, so that we're doing something a bit different. SF4, you take the time to draw the Lewis structure. You'll see that it has 1 lone pair of electrons and the 4 fluorines attached. So to follow the same process, we've drawn the Lewis structure, and now what we want to do is draw an energy diagram of the central atom. So for sulfur, with its 6 valence electrons, we are left with this. Now when you look at sulfur, again, just like in carbon, it's only prepared to make 2 bonds. And as we can see from this particular diagram, it's got 5 electron pair domains. So hybridization must occur in sulfur in order for the bonding in this molecule to be able to happen. In order to decide what kind of hybridization occurs, we need to look to our Lewis structure. We have a total of 5 electron pair domains, so we need a total of 5 hybrids. So S will give us 1, the 3 P's will give us 4. So in this case, we're going to need to access our d orbitals during the hybridization. Now, although they're not shown in this diagram at first, the d orbitals do exist. They're empty. Orbitals are just areas of space, so there's no reason for them to not exist within any particular atom. So we're going to hybridize these 5 orbitals. As with our previous example, the inner electrons remain the same. So we've got the 1s, the 2s, and the 2p are all there. And then we've got 5 hybrid orbitals. And you'll notice that the orbitals that we hybridize are all from the same energy level. So here's our hybrid orbitals, and let's look at the electrons that we have for placing here. We've got 2, 4, 5, 6 electrons. So when we place them in the hybrids, put singly, and we've got 1 pair. Now if you look and connect back to your Lewis structure, you can see that we expect 1 lone pair and 4 bonds, which is exactly what sulfur is prepared for. It's got 1 lone pair, and it's got 4 atomic orbitals holding 1 electron that is available for overlap with fluorine. So we can now show the electrons coming in from fluorine, overlapping with our hybrid orbitals. There we go. Now in some cases you might think, oh, I don't think hybridization needs to occur here. It won't be up to you to need to decide. You'll have either information in the question that will help you suspect that hybridization has occurred, or it will directly tell you that hybridization has occurred. Now there are different types of questions. If it asks you to show or describe the hybridization, you're going to want to show this kind of a process so you can see before and after and exactly what the hybridization looks like in the molecule. Sometimes you're just asked to state the hybridization. So if I'm asked to state the hybridization of SF4, my response to that question would be Sp3D, and that's all I would need to say. So I can just make that decision directly from the Lewis structure. Now when we have double and triple bonds, the hybridization is a little bit more unique. And we're not going to worry too much about modeling it in the same way that we did before. Okay? But I'm going to show you 2 examples because it helps to understand a lot about organic chemistry, which we will be studying this year. We're going to study ethylene, and ethylene is C2H4, and it's got a double bond between 2 carbon atoms and then hydrogens on either carbon. If you look at the carbons here, when we study organic molecules, each carbon is going to behave like its own individual central atom. So this carbon atom is trigonal planar, and the hybridization that's going to occur in this carbon atom is Sp2. Same with this carbon atom. It's going to be Sp2 hybridization. Now, as you know, there are 3 p orbitals, So when we hybridize and have Sp2 hybridization, what we have left are 3 Sp2 hybrids and an unhybridized p orbital. And these are all about the same energy, so these 4 electrons distribute themselves in a similar fashion. So what we have in each of these carbons is we have 3 Sp2 orbitals organized in a trigonal planar fashion around the carbon, okay, which is shown over here. So this carbon has 3 Sp2 hybrids, and this carbon has 3 Sp2 hybrids. Now what we also have is a 2p orbital that is unhybridized. And that 2p orbital will lie perpendicular to the plane. So if we flip this on its side, that's giving the carbon, you can see the wedge and the dashed line, and the wedge and the dashed line, and then the p orbitals are perpendicular to the plane. So in this diagram, they'd be coming straight out at you. Now what we have in this molecule is we have a sigma overlap between the 2 carbon atoms, a sigma overlap to the hydrogen atoms. So when we look at this bond, it's a sigma overlap, sigma overlap, sigma overlap, sigma overlap, sigma overlap. And then what we have is we've got these p orbitals that are unhybridized, so they're just a regular p orbital, but they have an electron in them. And that pair of electrons also needs to be shared. But these nuclei can't get any closer, so we can't have a sigma overlap. We need to have a pi overlap. So just like we discussed earlier on in the lesson, we're going to end up with a pi overlap, okay, where we've got sort of a hamburger bun looking thing where the electrons can be found above or below the plane. So this is the aftermath. We've got a sigma overlaps, and then we've got this pi overlap. Okay, so that's bonding in ethene. So as you can see when you study a molecule, anytime you see a double bond, there's always going to be one sigma bond, and then the second one will be a pi bond. Let's look at acetylene, otherwise known as ethene. Ethene has carbon with a triple bond to another carbon. And with this molecule that's linear, because there are 2 electron pair domains, you can see that the hybridization in the carbon this time is going to be sp, because there are 2 electron pair domains. So this time, we're going to take our 2s and our 2p. When we have our sp hybridization, we're going to have 2 hybrids that are sp orbitals. And then we're going to have, this time, 2 unhybridized p orbitals. So each carbon has this scenario. So we've got our sp orbitals, the red ones, going in either direction. And with those orbitals, we can have direct overlap. So I'm going to have a direct overlap with this orbital and with this orbital, okay, to the other carbon and to a hydrogen. And then for the p orbitals this time, I've got one set of p orbitals that are on the y-axis, and the other set of p orbitals is on the z-axis. So these are going to share through space, and then the ones that are on the z-axis are going this way. So we've got sharing from these 2, and then we've got sharing from these 2. Those strange hamburger buns end up going above and below and at the front and back of the molecule. So this is what bonding looks like in C2H2.